Right. So thanks again, Raimondo. So we move to the next speaker, Brandon Martin from Imperial College. Brandon will present network-informed restricted vector autoregression. So Brandon, you have 20 minutes. The floor is yours.
Okay, perfect. Thank you very much for the invitation. So yeah, today I'll be talking about network-based approaches to vector autoregression modeling. And in particular, I'll introduce the NIRVAR model, which is, so it's this joint work with my PhD supervisors, me, Haiku Gringu at Oxford, Alessandro Ratti, who's Imperial of Bologna and well known to VTSS, and Francesco Sanapacino, also at Imperial. Sorry. There we go. Next one. There we go. Okay. Sorry. Okay, so the setting we consider is a panel of multivariate time series, XIT, where, for example, I could label an asset and XIT the return on that asset, for example. And we model this panel as a var1, as shown here. And our goal is going to be to estimate the var parameter matrix phi in order to understand the co-movement between panel components, and also, once estimated, can be used for prediction tasks. However, phi is an n by n matrix of parameters, and so if n squared is greater than the number of observations t, we're in a high dimensional setting. So some approaches to tackling this include dimensionality reduction via, say, factor modeling, or sparse regression or network-based approaches. And we're going to be focusing on the network-based approaches in this work. So just I'll briefly touch on some of the related literature. And in particular, I'll talk about or briefly introduce the models with which we compare NIRVAR to in the application section. So there's a huge literature on factor models, a la Stock and Watson, and more recently, Fan et al. Have combined factor modeling and sparse regression in a framework that they call the Factor Augmented Regression Model, or FARM. Network-based approaches to VAR modeling have been studied by Knight et al., who introduced the Generalized Network Autoregression Model, or GNAR, and also by Baragozzi et al., who introduced FNETs, which is a similar setup. FNETs is a similar setup to FARM, but allows for dynamic factors, and they also have a novel estimation procedure. One other strand of literature that's relevant here is that on community detection. So the model of Gudmundsson and Brownless shares some similarities with the NIRVAR model we consider, and they use the estimated VAR coefficients to cluster the panel components. Okay, so for the there we go. For the remainder of the talk, I'll introduce the NIRVAR model, discuss its estimation, briefly talk a bit about its properties, and then talk about two applications, one in macroeconomics and one on financial returns prediction. So in a nutshell, NIRVAR is a var1 in which the var parameter matrix phi is modeled as the weighted adjacency matrix of some random graph. So let me briefly introduce random graphs and the particular types of random graphs that we consider. As usual, a graph consists of vertex set V and an edge set E. In a random graph, the edge set are random variables. So a latent position random graph is one in which each vertex has an associated latent position in some latent space Y, and the probability of an edge forming between two vertices depends only upon their respective latent positions. If the probability is given by the dot product between the latent positions, then we get the random dot product graph. And in this case, the adjacency matrix is a Bernoulli random variable with probability given by the dot product as shown at the bottom of the slide here. So as a cartoon of a latent position random graph, on the left here we have 6 latent positions corresponding to 6 vertices, and the probability of an edge forming between 2 vertices is given by the dot product between their latent positions. In the center, we have a realization of this latent position random graph, and that can be represented by the binary adjacency matrix shown on the right. One other type of random graph that's relevant to us is the stochastic block model, in which each vertex belongs to one of k communities called blocks. And the probability of an edge forming between vertex I and j depends only upon the block in which I and j are a member of. And we label this block membership using the function z. So zi labels the block of vertex I. The probabilities of the probability of edges forming between blocks is encoded in a k by k block probability matrix B. So for example, in the B shown here, we have 3 communities where the probability of edges forming within a block is much greater than the probability of edges forming between blocks. And on the right here is a realization of a stochastic block model with this block probability matrix. So stochastic block models can be represented as a random dot product graph in which there are k distinct latent positions, and the latent position of any vertex in the same block is the same. So we still have n latent positions, but only k unique latent positions. Okay, so given our stochastic block model, we can define the NIRVAR model as follows. So with k latent positions either given to us or sampled from a distribution, and a block label for each vertex, we sample an adjacency matrix from this stochastic block model, and where this this adjacency matrix is 1, we multiply by a random weight phi tilde ij, which is sampled from a separate distribution W, and then just the entry-wise product between phi tilde and the adjacency matrix A defines the VAR coefficient matrix. The key point here is that if there's no edge between vertex I and j, then the corresponding element in phi will be 0. So this gives sparsity to the phi. And from one perspective is that the random graph it induces 0 restrictions on the VAR parameter matrix. So as a pictorial representation, in this flow diagram, we have an example where there are 3 blocks, correspondingly 3 latent positions, and the realized stochastic block model shown here in the center is represented by a binary adjacency matrix. And then we replace the ones of this binary adjacency matrix with random weights, and the temporal dynamics of our panel of multivariate time series are modeled as a VAR1 with the phi matrix being this weighted adjacency matrix. So how do we estimate phi given some observed time series? So instead of trying to recover the edge set E, which is quite challenging, we instead aim to recover the latent community Zi. And the estimation approach that we take follows in 2 steps. First, we embed each panel component into a latent space. We then cluster those embedded points using a Gaussian mixture model. We define A hat as being the adjacency matrix of a graph that's fully connected within each cluster and has no edges between clusters. Secondly, we set phi hat, our estimated for our parameter matrix, to 0 if A hat is 0, and the remaining unrestricted parameters are estimated via ordinary least squares. So how do we actually recover the latent positions? So our approach is to compute the singular value decomposition of the sample covariance matrix. And the corresponding left embedding defined by y hat here will be our embedded points. An important question is how to choose the dimension of the latent space. And we approach this using tools from random matrix theory. In particular, we consider the Marchenko-Pastor distribution, which is the asymptotic distribution of eigenvalues of a random covariance matrix. And crucially, the Marchenko-Pastor distribution has a finite support. So any eigenvalue of our sample covariance matrix that's greater than the upper limit of this Marchenko-Pastor cutoff can be considered informative in some sense, and all eigenvalues that are below the cutoff are attributed to noise. And then we define the dimension of our embedding space as the number of informative eigenvalues of the sample covariance matrix. Then once we have our latent positions, we cluster them using a Gaussian mixture model. And so pictorially, the estimation procedure follows as such. We start with our panel, our observed panel. We compute the sample covariance matrix. We count the number of eigenvalues of the sample covariance matrix that are greater than the Marchenko-Pastor cutoff. This defines our latent space, and we compute a left embedding of the sample covariance matrix using a singular value decomposition. And then A hat is 1 if I and j are in the same cluster, and 0 otherwise. And the unrestricted remaining parameters are estimated using OLS. Okay, so some properties. I don't have a huge amount of time to talk about this, but I'll briefly mention that because the NIRVAR estimator is unable to recover edges between nodes in different blocks, it will be biased whenever those edges exist. The bias is characterized by this term C here. And one thing to note is that if A hat and A are actually the same, then C is just the identity and the estimator won't be biased. We prove that the NIRVAR estimator is consistent and is asymptotically normal around its biased value. The proof of this is follows along the same lines as the standard proofs for restricted VAR asymptotic normality, but extended to the case where the restrictions are maybe misspecified. Okay, so I'm going to talk about 2 applications of NIRVAR estimation. The first is to a macroeconomic application to the Fred MD monthly observations of macroeconomic variables. So our task, our prediction task in this case, is going to be 1 step ahead forecast of the industrial production index. So we backtest NIRVAR, which is the model we consider, against the farm model of Fan et al., the FNETS model of Baragozzi et al., and the GNIR model of Knight et al. So we do this every month from January 2000 to December 2019 using a rolling window framework. So NIRVAR and FARM achieve similar overall mean squared errors. NIRVAR is slightly below. We can see, so here the realized industrial production is shown in blue, and the estimated, the predicted industrial production is shown in red for each model. And we can see FARM and NIRVAR are much better at capturing they're much more flexible at capturing the peaks and troughs than FNETs and GNR. So the second application we consider is that to financial prediction, predicting financial returns. So we consider the previous close-to-close market excess returns obtained from the CRISP database. So CRISP is the Center for Research on Security Prices. And we consider a universe of 648 financial assets. Our task is to predict the sign of the next day previous close-to-close market excess returns. So that corresponds to predicting whether a particular security or asset should be long or short, essentially. Again, we backtest the 4 models using a rolling window framework of 4 years from 2004 to 2020. The results are positive for NIRVAR. So, for example, the Sharpe ratio, which measures the risk-adjusted returns. So a higher Sharpe ratio is better in some sense. So NIRVAR is a good bit higher than all other 4 models for this particular task. And we also look at the cumulative P&L of the 4 models. So on the left here, we see that NIRVAR does particularly well during the 2008 financial crisis and also during the early days of COVID-19. On the right, we are comparing the NIRVAR estimated clusters on a particular day to standard industrial classifications. So the usual manufacturing, financial, construction sectors that are given by SIC. And the takeaway, I guess, from this plot is that the NIRVAR estimated clusters are quite different. So they are picking up some some clusters that are very different from the standard clusters that people consider. Okay, so in summary, we've introduced a network-based approach to VAR modeling called NIRVAR, in which the VAR parameter matrix is a weighted adjacency matrix of a stochastic block model. The estimation framework that we present is particularly useful when the underlying network is unobserved, as opposed to some of the competing models such as GNR, which require the underlying network to be known. And some future work includes trying to deal with this bias problem by somehow modifying the method to allow estimation of the vertices between blocks, and also extending the model to a time-varying adjacency matrix. Furthermore, it will be interesting to see whether we can show that NIRVAR does in fact recover the latent positions of the stochastic block model up to an orthogonal transformation, which currently we can't claim. So it would be nice to be able to see if that is true. So thank you very much, and yeah, I'm happy to take any questions or comments. And here are the references.
Thank you very much, Brendan. So let me stop the recording and then